Dr. Jhuma Ray is presently the Assistant Professor of the Department of Engineering, Science and Management from RCC Institute of Information Technology, Kolkata. And she has obtained her bachelor degree from Calcutta University, completed her MBA in finance, and is a fellow from the Indian Institute of Management, Kozhikode. She holds a PhD in portfolio management with meta heuristics from National Institute of Technology, Silchar. She brings with her over 21 years of experience in academia and 2 years of industry exposure. She has achieved Outstanding Woman Researcher Award in 2025. Congratulations, ma'am. She is a winner in Portfolio Management Research category, Venice International Women Awards 2025. She has also obtained Best Paper Award for contributions to intelligent financial systems and optimization techniques. She has also obtained the Best Citation Award for excellent achievement in delivering presentations. She is a regular contributor to Delhi Tech Times and Re-Atal USA on fintech innovation, AI, and digital transformation. She is a selected speaker at Ideathon 2025, and she has an ongoing collaborative research under the Balak Brahmachari Research Society, and she has featured Josh Talks. She has featured as Josh Talks speaker, and she has given very uh, inspirational talks across all disciplines. So we welcome you once again, madam. And now over to you, madam. The session is
Thank
yours.
you. Yeah. So thank you, Navamita. Navamita, well, she is also a Bengali as myself, and both from West Bengal and Kolkata. Navamita right now is in South Bengal, central, yeah, Kolkata. Myself in North Kolkata, it's raining heavily and tremendous rain is
And
falling.
ma'am, can you just increase your volume? I mean, it's sounding a little bit low.
Are you able to hear me? I'm on the, yeah.
Audible, ma'am, but slightly the volume can be raised.
Uh, it's already my volume. It's yeah, just
Okay, okay, okay.
yeah.
I think the participants, I hope all of them can hear you.
Okay,
Yeah.
okay. Without wasting any more time, good afternoon to everyone, one and all over there. And it's a great honor to be speaking at this 1 week online faculty development program. And it's a great honor to be a speaker, which is the program which has been organized by Heritage Institute of Technology in Kolkata, and as well as in collaboration with AMIEE Association. I would like to thank all the organizers as well as the program conveners for inviting me to share my insights on optimization techniques in engineering design using genetic algorithm, as well as particle swarm optimization and artificial neural networks. Now, why did I choose to talk on this matter? Because it's a domain where I prefer to talk lot and lot, because it's a domain of my research field. And as engineers and researchers, we are constantly actually solving problems, and optimization is at the heart of engineering innovation today. So today we will be exploring how intelligent algorithms are revolutionizing this entire process. And so first, starting with my slide, let us delve into meta-heuristics, which from the backbone of many modern optimization, techniques. What meta-heuristics are broadly to speak about are the high-level problem-independent strategies that are designed to efficiently explore different search area or search spaces. They do this by combining these different lower level heuristics. So heuristics mainly we find in the financial domain, where we apply for finding out the risks or detection of risk, achievement of different techniques like within the portfolios, etc. Here, this high level problem independent strategies, which I mean to say about the meta heuristics, they are designed to achieve a balance between exploration, that is researching the new areas of the solution space, as well as the exploitation, refining different known good solutions. So these methods are incredibly powerful, as well as spatially when dealing with complex nonlinear or multi-objective optimization problems. And if we feel like, yes, we need to, encounter this to the electrical engineering design, which is the basic interrelationships for this week-long FDP. So it's all about which we can fit into the circuit layouts, power flow control, or fault diagnosis. So there are several major familiarities of meta-heuristic algorithms. And if we find this in the evolutionary algorithms, which has been inspired by the process of natural selection, we can find swarm intelligence techniques, which include this genetic algorithm, differential evolution, and as well as the evolutionary programming. All of these simulate collectively, on the collective behavioral pattern of natural systems like flocking of birds or fish schooling. Coming to other types of swarm intelligence like this cooling, which mimics the physical process of heating, slow cooling of metals to remove defects and reach a minimum energy state, as well as which is ideal for escaping local optima. There can be other techniques too, like the taboo search, which I have mentioned over here, and this actually uses memory structures to avoid cycles and guide the search intelligence, by forbidding the different visited solutions. So there can be these different sorts of techniques which can be used within the meta-heuristics domain. Now, if we consider these properties of these meta-heuristics, as we have already introduced the meta-heuristics, so first, the meta-heuristics are not direct solvers. Instead, these actually guide the search process. And these procedures intelligently explore the problem search. So this can be done using rules inspired by or rules inspired by society or rules inspired by physics. So unlike exact algorithms, they don't guarantee the global optimum, but aim to find out the high quality, near optimal solutions efficiently. And also, the key strength of these meta heuristics would be the ability to, finding or navigating the complex search spaces. So these meta-heuristics can efficiently navigate the complex search spaces, whether it's multidimensional or noisy or non-convex, making them ideal for a problem where traditional techniques. Coming to the third one, so these are typically approximate and non-deterministic. This might give slightly different solutions on different runs, and that's why this design or this randomness helps in escaping local optima or broadening the search areas. So meta heuristics are actually problem independent. Now, if we consider this slide, find there is a quotation. So if we can draw, if you all can draw your attention to this insightful quote on this slide, which actually states about genetic algorithms which are good at taking large potentially spaces and navigating them, looking for optimal combination of things and solutions which one might not otherwise find in a lifetime. And this actually captures the very past essence of genetic algorithm, which is all about like genetic algorithm are inspired by the natural process or procedure of natural selection procedure, which relates to the biological mechanism behind evolution. Now, these actually mimic low nature or, which are evolving organisms to adapt and survive. In the same way, genetic algorithms would actually evolve solutions to optimization problems, generating the different or after one after the other generation, they would actually evolve issues. You can find that yes, this genetic algorithm is been discussed upon. So these are categorized as direct search algorithms, and which actually do means blindly searching the space area. Instead, using any biologically inspired mechanisms to intelligently guide the search towards high quality solutions. Rather, John Holland in 1970s, a professor of University of Michigan, he developed this concept. And his dual motivation was firstly to understand how adaptive procedure could work in natural systems and how organisms would be adapting or evolving into or thriving into. And secondly, it also visions to lead to the development of a class of algorithms that could adapt or learn the things evolving time over. So making this ideal for solving ill-structured or dynamically changing optimization problems. And these are actually efficient or effective. And these are meant for wider range of problems, not just engineering, but also in machine learning, pattern, recognition, data mining, or combinational optimization problems. So it's particularly useful in multi-objective optimization. Even myself within the area of finance, when I applied this in my research domain, initially I started with my research with a single by application of all these meta-heuristic techniques, PSO, SEO, and colony optimization, differential evolution. But later on, I also objectified on multi-objectives, that is into the financial domain, finding out the risk and returns, ascertaining risk and returns at the same time. So it's particularly useful in multi-objective organization optimization, and where trade-offs are required to be balanced across multiple goals. So if we relate to electrical engineering, balancing the cost, efficiency, and safety, it can be used widely into the businesses and science, as well as electrical engineering for designing, controlling, tuning, and reliability enhancement. So, this essence of GA actually serves as a powerful tool that bridges this biology or computation with unmatched versatility across disciplines. If we come to the next slide, see, here we can find out the, different components of GA. Now, let us break down these key components which actually make up GA algorithm. Understanding these elements is very much crucial because each step of this GA procedure would actually correspond to the biological metaphor. And implement a GA, we need a problem to solve, and following components should be looked into. If we find the first component, which I have stated about encoding technique, which actually do mean the gene or the chromosomes. And here the gene or chromosomes, these actually are the foundation. So this technique is the foundation where we must represent the solution in a form that algorithm can manipulate. And like typically like strings or bits or real numbers or permutations, think of this as DNA in a biological system, which each chromosome actually encodes a candidate solution. Each gene represents a variable or trait of the solution. And if you find the next one as the creation, which is the initialization procedure, this actually is the starting point. And this starting point is where an initial population of solutions is randomly or heuristically being generated. So just as nature begins with a diverse gene pool, a good genetic algorithm would actually start with a diverse set of candidate solutions. So this is actually required to ensure a wide exploration over the varied search space. Coming to evaluation function, which is all about the environment, and this is also known to be as fitness function. I hope you all know about this. So this is where each chromosome is evaluated here in genetic algorithm. So how well does this problem actually the solution would perform? And if it is like, so this step actually mirrors testing an organism's adaptability. The better the fitness score would be, the higher would be the chance of being for the reproduction procedure. So coming to the next step, it's all about reproduction. And reproduction, when we state about, so this step actually selects chromosome for crossover based for the fitness. So we have already mentioned about the fitness in the evaluation function. And when it is based on this fitness, as well as the popular selection would be the technique, including like tournament selection or ranked based selection. So it would actually ensure the better performing solutions having this higher probability of passing their traits. And coming to the genetic operators, when mutation, recombination, so this is the crossover mutation function, and where combining of the genes from two parents to produce or more offsprings can happen, or introducing the random changes in the genes, helping the algorithm exploring new areas and maintaining diversity. And whenever we speak this meta heuristics, it's really does feel like much interesting, because when we are relating to the real life genetic behavioral pattern of organisms, or like flying behavioral patterns, which will come in the next technique like PSO, or the ant colony optimization, where the behavior of the ants in the search of food can happen. So all this comes into our. So coming to the next one, the parameter settings, which is all about this, practice and art, and it is about the hyper parameters. These elements of the population size, or what we have mentioned in the crossover and mutation rates, or the number of generations, actually does depends on this parameter settings, or the particle and art, which I'm mentioning, or which we mention into these components of genetic algorithm. Uh, Now, the simple algorithm would actually be considering about the simplified working structure. See here, which actually is in the essence of a loop of evolutionary refinement. And if we go through each step, we can find how the initialization of the population occurs at first, the first step, which is creating the diverse set of initial solutions actually, and usually randomly being generated. So this set would be called to be the population under each member, or the chromosome, which presenting the candidate solution of the problem, or the for this problem, for any of the problem. Now, this population is the next one, where we actually evaluate how good each solution is using as a fitness function. So whatever fitness function we are putting into, that needs to be evaluated, and this is actually determining how likely each chromosome for reproduction. And in engineering application, this could be minimizing the energy loss, maximizing the efficiency, or achieving the cost reduction. So criteria, while termination would not be, this would be the main loop, and this algorithm will continue to evolve the population until the criteria would be met. So until and unless the termination criteria is met, the loop would be continuing. And common stopping criteria would include like the maximum number of generations again, or a solution of acceptable quality which is required by the researcher, or in fact the successive generations over which any improvement can be done. That is, no improvement if it is impossible, or impossible means if any improvement is impossible over a successive generation, that is been selected. And selecting of the parents for the reproduction would also be the selection of the typically the parents. So here, how the ranking system or rank selection or tournament selection would happen. These are chosen through selection techniques. Combining this all, after the performing this combination and mutation, so crossover and mutation, when it is being done, combining both these two, the evaluating population can be happening. So after the new generation is formed, we can re-evaluate the fitness function again. Function which is, which is already been setted, this can be again re-evaluated, and the process actually can be continued with newly evolved the population. So in short, this is actually a loop, and this loop would contain the selection, crossover, mutation, evaluation. These are all mimicking the evolution and allows the algorithm to iteratively improve towards the optimal or near optimal solution. So once this solution is being reached to, it can be stopped. And in the section, we can also explore the particle sum optimization, which would actually show a very different but equally powerful nature inspired algorithm. Now, coming to this slide, again, when GA cycle of reproduction can be, spoken about, it's all about visualizing the core engine that GA algorithm, and it's all about the cycle of reproduction, wherein we can find that, yes, which you can find in this slide, it illustrates how the population actually evolves over successive generations. Each block represents a stage, and in the genetic life cycle, the arrows show the flow of individuals and or the chromosomes. Through this process, how it goes on, we can see that the population at the center of this cycle, you can find the current generation of the candidate solution. This is the population. This is the working pool from which the parents are selected and to which a new offspring can be added or are added. And coming to reproduction, from this population, we can select individuals or one can, this can become, parents. So the selection typically it is biased towards the feature individuals. And this can undergo reproduction, create children using crossover also, and the genetic mixing mechanism would continue. Modification can happen. The newly formed children are then subjected to modification, which actually refers to the mutation process. And this introduces the random variations, sometimes small, sometimes significant, to ensure the population remains, which actually would remain diverse. And coming to evaluation, it is the next modified children which are evaluated using fitness function. So we can assess how well each of them actually solves this problem. So this is critical. It tells us how or which offspring are promising through enough, these are enough to survive. And back to the population again, if it is been seen, the evaluated children are now ready to re-enter the population. And depending on the selection strategy, they may replace weaker individuals or may be merged with the existing population based on the criteria or the fitness function. And coming to discard, so discard is finally individuals who are not fit enough to have become which are obsolete, which have become obsolete in the evolving landscape. So these have been discarded, making room for better size and maintaining a manageable population size. So this cycle actually continues generation after generation, and until the algorithm meets its termination condition, this convergence has been reached or maximum iteration has been reached, this would be continuing. So the essence of GA operates like its self-correcting feedback loop, using like reproduction, variation, and evaluation to gradually improve this quality of solutions. And it's see how beautifully it's described the exploitation of the good solutions and exploration of the new possibilities. No, so a fundamental this is a principle which can underpin all evolutionary algorithm. So if you see the optimization using particle sum optimization technique, which are latter, which also mentioned to another fascinating technique, and it inspired by the genes, but also by the social behavioral pattern of the organisms. Now, coming to our next slide, we can find the population which actually is stating about the fundamental components of genetic algorithm. And population actually is referring to the set of all the candidate solutions that exist at any given generation. Now, each individual to be as chromosomes, and we be representing the potential solutions to the. Now, the way we represent these chromosomes, their data structure or encoding is very much crucial. And this is crucial because it affects everything from crossover to mutation as well as evaluation. Now, let us look into these common representations of the chromosome. There is the bit strings, and these are the representations which actually sequences zeros and ones, and used often in the simple combinational problems like binary encoded parameters. If we see the real numbers when we are dealing with continuous optimization problems like tuning or controlling tuning a control parameter or designing analog filters, we use these floating point numbers. Example like this, we can 43.33, which we can use. And these partitions of elements, these are like traveling salesman problem or routing this and scheduling, where this order actually matters. And if you consider the list of rules which are useful in the expert systems, the fuzzy logic controllers or rule-based design, where each gene represents a rule. If we consider these program elements in genetic programming, actually chromosomes represent actual program codes, and or we can say about the decision tree. So these are highly expressive but more complex to manage. Example like logic tree, symbolic equations, or flowchart elements. And any other data structure which is been considered, this is all about the flexibility. As this meaningful crossover and mutation operations, we can use any data type or structure, or which would represent the graphs or trees or hybrid encodings, or in fact the matrices. So this is all about this any data structure, and about the choice of encoding depends on the nature of this problem. Whatever the problem is, a well-designed representation makes it very much easier, because for this genetic algorithm to evolve towards better solutions, it facilitates the effective genetic operators, and the evolution actually starts, and yes, it reflects the diversity, drives discovery, as well as it actually ultimately leads to near optimal designs. Now, if we consider the reproduction here in the next slide, it is where the selection it determines which chromosomes would be, which chromosomes from the current population would be selected or chosen to contribute their genetic material to the next generation. And the parents would be, parents are actually been selected from the existing population. So these selected individuals would then undergo the genetic operators like crossover and mutation, as I have already stated, to generate the children or these, offspring solutions. Although the parents are selected randomly, their probability of being selected is not uniform. This is, yes, the technique, and where rather it is by proportions to their fitnesses also. So this process actually ensures the better solutions, having higher chance of being passed on the next generation. So where we can find the entire so a balanced selection strategy, it is all about the modification through crossover and mutation. Coming to the chromosome modification within this genetic algorithm, this stage is the key to introducing the variability or exploration into the search area. And if you can find this, where actually generating new solutions are been happening by altering the genetic materials of the children. So modification module and what comes out of these modified children are ready to be evaluated. how this modification actually happens. Modifications are, stochastic. They are these are probabilistic. In child uh, would have a certain chance of undergoing one or more genetic operations. So there would be mutations, definitely. So this is a random, alteration of one or more genes in the chromosome. And again, it's all about change, flipping, which I have showed in the bit from 0 to 1. So flipping a bit from 0 to 1 would happen. Value in the vector can happen, would be happening along with that. Swiping with the cities in the routing problem, that is what can be happening. So mutation is essential, and coming to or recombination, where this operation combines parts of these two parents of chromosomes. So 1.1 crossover for bit strings, or arithmetic crossover can happen for real valued chromosomes. Yes, for mutations, there can be partially matched crossover. And crossover would actually promote inheritance of good traits, or it would actually accelerate the search toward better regions. In practice, this crossover and mutation are applied selectively. Sorry. If we come to this next slide showing only the mutation function, so we can focus into the different concepts here, like the local modifications being done and local search operators happening. So it performs small or random changes in the chromosomes, and these changes would help in exploring new regions. These now, if you can think of the biologically equivalent or of a like or any copying error or a random gene which can be flip that occasionally. So result would be in favorable trait, right? So for binary representation, mutation involves flipping bits, changing this 0 to a 1 or vice versa. And it can be for this real valued encoding, the mutations may involve adding a small random value to a gene within some defined bounds. For permutations based problems like routing, scheduling, or mutation, this might involve swapping of two elements, like reversing a segment or rotating positions. This can happen, and preventing this, convergence, premature convergence, I would rather say, because it is done for by ensuring that the population does not become too uniform, or it would be stuck in a local optimum. So it allows the GA to recover if a good solution are lost, or if the population starts converging too quickly without meaningful improvement. This can be, the best way to get equipped from that. So in a broader frame or perspective, this genetic diversity would actually promote adaptability, and it would actually strengthen the algorithm, one algorithm's ability to escape this local optima and continue the improving quality of this algorithm. So up next, we'll look into the mutate and the crossover also. I'm going over this slide a little fast, because yes, it would take much time if I go into all these slides, into the depth of the slides. So if we consider this crossover or recombination in a fast manner, so it's all about the two parent chromosomes which are selected from the population, usually based on their fitness, and this crossover operator would actually combine portions of both the parents. So there are various types of crossover strategies which would depend on this chromosome representation. For binary strings, a single point crossover would be there. A point is selected on this parent string, and everything after that point is swapped. 2-point crossover can also be there. For real valued chromosome, arithmetic crossover. For partially matched like crossover, for this permutation based problem can be happening. So there can be order combination also, so order or cycle crossover. It's very important, because it is This crossover is the creative engine. And this is the creative engine of this genetic algorithm, which is known in the bookish form, and it is actually generating diversity. And if we find this, the driving and the search toward the optimal regions or the solution space is happening due to the crossover or recombination. Coming quickly to the next slide, the evaluation, which would actually is stating about assessing the quality of the newly generated offspring. In other words, determining how good a candidate solution can be in solving the problem at a space. So fitness function can be changed, the fitness can be changed and found out that yes, if we can reach to our optimum solution. Coming to the deletion portion, yes, it's the part where we can find that uh, we can actually come with this, essence of deleting or deletion of is all about the pruning of the function, and we can remove the unproductive branches, and we can go so that the algorithm can grow stronger and explore more fruitfully. So we aim to retrain the we can remove the weakest one, and we can maintain an adaptive and we can also evolve the population, or evolving this population would actually get the better or with best gene or best generation we can find out. Looking into the next one, it's the illustrative example. Actually, it states about the three functions. If you find this behavioral pattern of the birds, it's all about flocking of birds. It's an example where the hoarding is there, the fish schoolings. So it's all about the different behavioral pattern. It's related to the genetic behavior of them these organisms. Consider these examples. Yes, these are the different example of the problem solutions, and these are the solutions to the problems of the genetic algorithm, which we can find. Quickly running with this, which issues one practitioner can, while being a genetic, algorithm practitioner, what issues can be there. Now, while these algorithms are very much powerful, we know these are also flexible, but practitioners can often face several challenges, like encoding the solution, choosing the right representation, whether binary or real valued, or permutations, or greatly which would be affecting the algorithm's performance. So these can be there. There can be issues designing, with designing the fitness and mislead the search also. Tunings, so population size or the mutation rate can be also a big problem. So there can be also issues which a practitioner can find, and the benefits overall can be the versatility, and this would actually be that GA don't actually require derivative information, making this like non-differentiable, making this a noisy or black box function. So gradient needed over here. And if it is, because it is the global search, it is having global search capability, they would actually explore, this can explore the search space broadly and less likely to get stuck into local optima. Finding this, in short, this flexible, powerful, as well as adaptive, and this can make highly effective, or this can be highly effective for the for solving the real world or high complexity problems. Now, when a researcher or a practitioner would be using these genetic algorithms, now genetic algorithms are not a one size fit, which would fit all the solutions like that. So it can be used when the search space is very large, the problem is very much complex, or it been poorly understood. So especially when traditional method actually struggles over there, finding algorithm can be the efficient solution to that problem, and application of genetic algorithm. So objective function when it is non-linear, when it is discontinuous or multimodal, definitely genetic algorithm can find a solution for that. And yes, conflicting constraints can be there. So whenever one is facing a problem that's very much hard to solve analytically, or too complex or deterministic methods are to be applied, so that's where one can consider this genetic algorithm to be applied. Uh, yes, I'm not going to this portion. So our genetic algorithms, these are, overhyped or not. So a common tongue in cheek like question, this is a question which is always there. So if we can uh, explain this, so it's a beautifully quote which actually captures the real value of GAs, and not in the frame of fortune or yes, but it is the immense practical utility across domains like engineering, finance, biology, or AI, and much more beyond. So this can be applied. So this is the richness which lies in the relevance of GAs. Sorry. Coming to the new slide, new technique, and let's now dive into the second major meta-heuristic technique in our discussion, that is all about the particle sum optimization. Now, if a genetic algorithm inspired by biological evolution, then this PSO, actually this particle sum optimization, draws its power from social behavior, which especially from how the swarms in nature operate. Just think of the flocking of birds searching for food, or a school of fish reacting, or reacting to the predators. So there's no central leader, yet they move in. See, they move in a highly coordinated and intelligent manner. So PSO is based on the kind of distributed collective intelligence, and it was it's been detected, or it's been brought up by uh, James Kennedy in 1995, and Everhart, an electrical engineer only. Now coming to our next slide, which actually states about the PSO, and it states that how this PSO particle sum optimization would actually deal with. So PSO scheme, it's very simple, yet it's very much highly effective also, and it combines with the global exploration and the local exploitation, which allows the swarm to intelligently search for the best solution. And yes, uh, up next we will look into the mathematical equation actually that governs with this behavior. And if we see, you can see here that, see, if you find the best known position, and yes, it speaks about the different bird or a particle or the food or the solution, and it's about the solution or the fitness which has been achieved. Now a position which is there, which represents the current solution, and a velocity which actually, and a record for the personal based solution is been recorded, or knowledge of the global best been found by people. And the representing potential solution would be the applying to the solution space area. So this needs to be adjusted, and its movement is based on the own experience or experience of the other swarms. So the goal is to the is for modeling the social learning, or and applying it to the numerical optimization. These GAs, genetic algorithms, PSO actually does not rely on crossover or mutation. Instead, it models a collection of particles, which each of which would be representing the potential solution. Now, the PSO scheme, this actually states about the best solution, which I have stated, and the P-based solution, or the which is known to be the particle based, or the other one, the position based and the global. And if we say about these two, so P-based is all about the best known position so far. And adjusting all these positions and velocities over time, it can also find the best position in the entire swarm. So that is all about the global based. And these creates a balance between the individual learning and balance between the individual learning and as well as the social sharing. Particle updates its velocity based on this P based and the G based, and this would actually move into the new position. Now, PSO search scheme would actually state about this global optimization or global the local optimal values to be found out, and it states about the updating the velocity. See here, when we come to these or two key equations of these, here how the velocity updation is being done. And here we can find that inertia weight, which controls the influence of the pretty exploration. Coming to the C1, 2, this states about the cognitive and social coefficients. So these are all about the random numbers between 0 to 1. And 0 and 1, yes, these random numbers are being selected, and the best position, P-based or I-based, is also been found out. And after that, the global-based solution can be evaluated. So it's own learning and it's about the group learning. So P-based would be about the own learning and the groups learning about the G-based, and where the randoms would be avoiding getting stuck. So this is the B. And position update would be happening in both the cases. So this is how these two equations together would be guiding the entire swarm through the space search and search space and balancing the exploration or exploitation area. And inertia weight would actually play a critical role. So inertia weight would be this, which would be, here, which would be encouraging the exploration, and if it is been lower, it would be encouraging the fine tuning or exploitation. So in many versions, this W is dynamically adjusted during the run for better control. So this is simple yet very fast adaptable also. So here we can find that how the is been done first. This algorithm would be step by step. It states about this how initially the swarm initialization of this swarm is done when we begin by randomly initializing the position and velocities of these particles in the search space. Then how the evaluation is being done. So how the fitness is being computed of each particle objective function which we have created. Based is also been done, and based is done. Each particle when been updated with its personal based position, and the swarm tracks. So swarm would be tracking the global based position. Updating of the velocity would also be done using the particle, updating equation. So we would be calculating the new velocity and updating the position of each particle. And finally, the repetition would also done. So here, in short, this PSO is all about the loop, evaluating, updating, moving it, repeat itself. So it would be done in a dynamic manner, adapting to the learns from both the individual experiences or the collective wisdom also. So this application would be all about it can also explore some many or vital applications can be done in the electrical engineering also. So how it could be done, I will state about that. So I would quickly skip this clustering algorithm, which actually states about each particle, how this represents a set of cluster or centroids. the goal of this to optimize the central so that the intra-cluster distance has been minimized. I would rather, I'm skipping this and how the achievement of the experimental results is done here is once the PSO algorithm has been implemented, we run multiple experiments to test its performance, and these are been done in the convergence by convergence speed or accuracy of the solution is being maintained, and we compare the results uh, against the benchmark or other algorithms to validate the effective or effectiveness of the PSO in solving the target problem. Now, there are also certain issues I have stated for the practitioners, which while using the GA also. So while PSO is very much simple, as I have stated, and effective, but practitioners may also face some challenges like premature convergence or parameter sensibility, like using the inertia weight or learning factors. And yes, careful tuning and hybrid approaches are often required to overcome these limitations. Now, certain benefits for usage of these PSO algorithms, because PSO particle sum optimization actually do offer several compelling advantages. Like PSO is very easy to implement with just two main equations, as I've stated, for velocity and position updates, and fewer parameters to tune. These can be applied, and these have very fast convergence rate also, where we can find that PSO often in continuous and real valued optimization problems, and it's very much flexible enough and scalable. So it's a robust procedure. In overall, it's efficient and versatile also as an optimization technique, and it's well suited for both this academic research or real world engineering problems. Now, the artificial neural networks. So now we have inspired optimization through genetic algorithms and particle. Shift our focus to the third pillar of this session, and it's all about artificial neural network. Simply to put, these artificial neural networks are computational models, which actually is inspired by the structure and functioning of the human brain. So these are designed to recognize patterns, learn decisions, even in complex nonlinear environments. Just like our brain learns from the different experience by strengthening certain neural connections, artificial neural networks learn from data by adjusting internal parameters like the weights. And there can be the input layer where we feed in our features or the data itself. There can be the hidden layers where actually the learning and transformation is taking place, the outer layer which delivers the final or the classification of result is being done. So each unit in this network is called neuron, and every neurons has an associated weight. So because this, unlike traditional algorithms, this artificial neural network don't require explicit programming. So they learn from examples. This particularly it is useful in function approximation, series forecasting, pattern recognition, control systems. There it can be applied, and in context to electrical engineering, this artificial neural network also been successfully applied in cases of load and energy demand forecasting, fault detection, classification in power system. So this has been done, or controller design for dynamic systems. So in short, wherever prediction, control, or classification is required in a complex environment, artificial neural network can be a perfect choice. Yes. So applications, as I have said, where it can be applied, it can be most widely tooled across various disciplines, not only yes, it can be across the disciplines due to their exceptional learning and generalization abilities, and it can be if we in the allied domains like electrical engineering, it can be load forecasting and energy demand prediction process. Also, one of the most critical challenges power systems, where actually the accurately forecasting is being load. So artificial neural network are trained on historical consumption data and external variables like temperature or time to predict future demand can be done. This can be done by enabling the efficient management or this reproduced operational. Next slide, we can find the different models of artificial neural networks. And artificial neural networks actually come in various architectural models. These are suited for different types of problems. This can be feed-forward network problem, neural problem, or this can be recurrent neural net. Information flows in one direction from this in groups where this can be used, widely used in regression and classification, which can be stated to be as feed network. And it can be so the problem where each model has unique strengths, and is chosen based on the nature of the data. And so this conventional neural network, which has been originally used in image processing, but now applied in power grid monitoring also, or is also. And if we think about the neural network, so it can happen where they have the feedback loops and allow the memory of previous inputs, so which is ideal for the application of load forecasting or signal prediction happen over there. Now, neural network, this neural network is a computational model and which is inspired by the human brain. As I have stated, it consists of the interconnected layers of nodes, or which is also known to be as neurons, that work together to process as well as learn from the data. So each neuron receives inputs which applies the weights, which passes through like activation function and also layer. And if we find the biological neural network, we can find, before we dive deeper into this problem, the biological neural network between or behind the artificial neural network. So how it has been evaluated, a journey which has come to span over several decades of it. How this artificial network and biological neural network can be related, it's been shown. And the application of this neural network, artificial neural network, can be done in load forecasting, like power demand using historical data, or fault diagnosis, like classifying and detecting the equipment's failure in real time. Now, this I will also explain in my later slides. And yeah, going closely to the end, because I understand time comes. Now, how this application can be done into electrical engineering. So as I have already mentioned here in my lecture session, that artificial neural network can be applied for load forecasting, predicting short-term and long-term energy demand. Yes, this can also happen or it can be applied in fault detection or diagnosis for classifying and locating the faults in transformers or lines or motors. And yes, it can be done for adaptive like controlling system, implementing neural based controllers for dynamic systems. So yes, this can for the different segments like renewable energy forecasting can be done, predicting the solar irradiance or the wind speeds to optimize or integrate So the integration procedure optimization of this can be done. The power quality monitoring, like the identifying the disturbance like sags, swells, or harmonies in time. This can also be done. So yes, this can be applied. And if we application of genetic algorithm, so genetic algorithm is also, it can be related, or it can be applied in the engineering, electrical engineering especially. So here also the reactive power control, which is a major issue in smooth flow of the electrical power, both at the distribution side as well as transmission side. This can be handled, and many artificial intelligence techniques, or this can also be used or put into use for controlling this reactive power through this application of GA. And power flow can be, yes, definitely it can, which can be considered as to minimize next. And we can also find this objective function being represented by the generation of loss, or the generation cost, and GA or genetic algorithm, which stands to be the best technique for solving the optimization technique when being compared to the conventional or traditional methods. And when we find this PSO, particle sum optimization, it is how, or it can be absolutely fitting to the electrical engineering disciplines, while the economic dispatch method comes into use, minimizing the fuel cost while meeting demand, or the PI, improving the control system response. In fact, the microgrid management can also happen, balancing the cost, or power flow in the distributed systems can also happen. So yes, optimal control variables for efficiency and stability can be done by application of these particle sum optimization. And it's really very interesting that we can the behavioral patterns of these birds, flocking of birds, or fish schooling of the fish, or the behavioral patterns of any other organisms, and the GAs or neural network, how this can be applied into the different fields, not only in the field of computational science, but also in the allied disciplines, and as well as in electrical engineering. So I would mention about the electrical engineering because today we are having this FDP for 1 week long time, aimed or targeted for the electrical engineering section. Or myself being into the field of the computer science, I related my basic all this knowledge, or knowledge of meta heuristics, to the field of finance. Basically, in today, it's been used for identification of the risk amount in the different portfolios. So finding the optimal values of risk being allocated in the portfolios, it was my target area. So how it applied to different other fields is being stated.